Look at a standard university syllabus for signals and systems, and you will see a dense wall of partial differential equations and infinite series. Relying entirely on brute force algebra is exactly why this class has one of the highest failure rates in engineering. The entire discipline exists to solve one specific problem, predicting exactly how a linear time invariant, or LTI, system will alter a signal passing through it. Calculating those alterations natively using raw calculus is incredibly inefficient. Instead, engineers use mathematical transforms as translation tools to move the problem into environments where the math is easier to compute. We translate the signal between three distinct operational environments: the time domain, the complex frequency domain, and the frequency domain. If you map out the high-yield topics on an exam, trying to memorize 50 isolated integral formulas is a trap. The most efficient way to pass is to master the physical geometry behind these 5 core operations. Once you know how to spatially translate a signal from one domain to another, you can guarantee a system will behave predictably before you ever solder a single component. We start in the time domain. This is the native environment where an LTI system processes inputs through a mathematical operation called convolution. Algebraically, convolution is expressed as an integral that combines an incoming signal, x of t, with the system's inherent impulse response, h of t. This diagram visualizes convolution. We convert the time axis to tau, then flip the impulse response backward across the origin. We slide this reversed response forward toward the stationary input signal. The physical geometry where they overlap is their actual interaction. By integrating this illuminated overlap area at every position, we dynamically generate the final output waveform flow. The most common failure point in exam analysis happens right here. Students will try to evaluate the entire process using a single static set of integration limits. The physical shape of the intersection changes continuously as the signal slides forward, meaning mathematical limits of integration must be recalculated for each distinct phase. If you apply one set of limits across the board, your output equation will describe a shape that doesn't actually exist. The entire convolution sequence is completely rigid. Plot the variables, flip the impulse response, slide it across the input, multiply the overlapping areas, and finally integrate. Time domain analysis comes down to a spatial operation. You are measuring exactly how the geometric footprint of an LTI system alters an incoming signal as it sweeps past. While graphical convolution works well for simple shapes, calculating higher-order differential equations directly in the time domain is slow and prone to algebraic errors. To bypass this, we move to the complex frequency domain. We use the Laplace transform for continuous time signals and the Z-transform for discrete digital data. These transforms take difficult calculus derivatives and integrals and convert them into standard algebraic multiplication and division. However, writing out the algebraic equation of a transform means nothing unless you establish the exact mathematical boundaries where that equation holds true. This maps the region of convergence, or ROC, the valid zone where the Z-transform produces finite numbers. We plot the system's roots, placing poles marked with an X. Around the origin, we draw the unit circle. The shaded ROC projecting outward tells us if the system is causal and stable. For a discrete system to be causal, meaning its output depends only on present and past inputs, the ROC must project outward, existing outside a specific circular boundary. Stability requires a standard known as BIBO. Bounded input must yield bounded output, rather than growing exponentially until the system breaks. You can verify this visually. If the shaded region of convergence entirely encompasses the unit circle, the system is stable. If the ROC misses the unit circle, the system will eventually fail. This reliance on pole placement introduces a major trap when applying the initial and final value theorems to find steady-state behaviors. Warning tone: if a discrete system has poles sitting on or outside the unit circle, applying the final value theorem is mathematically invalid. The formula will yield a number, but that number will be false. You must physically locate your poles and explicitly write down the region of convergence before attempting to calculate steady-state values. Evaluating the complex frequency domain is an act of mathematical cartography. You are drawing explicit geographic boundaries to guarantee your system remains stable in reality. The third environment is the frequency domain.
Here, we extract and analyze the individual harmonic frequencies that make up continuous periodic signals. The Fourier series proves any repeating waveform is just a combination of sine and cosine waves stacked together. Calculating these is tedious, but identifying signal symmetry eliminates half the work. If it mirrors perfectly across the vertical axis, it has even symmetry. Even functions are composed entirely of cosine waves, meaning you can instantly bypass the sine calculations. Conversely, if the signal has odd symmetry, the cosine terms are mathematically eliminated.
This frequency spectrum graph maps a baseband signal's maximum outer boundaries. When taking discrete samples, the entire spectrum automatically copies and repeats at set intervals. To flawlessly reconstruct the original signal, we must obey the Nyquist theorem. The sampling rate must be at least twice the signal's maximum frequency. If the sampling rate drops below that exact mathematical threshold, the repeated frequency spectrums are forced too close together. Their outer boundaries physically collide. This destructive spectral overlap is known as aliasing. When those high and low frequencies merge, the data is completely corrupted. You cannot filter it back out, and the original signal is irreparably destroyed. The frequency domain dictates the strict mathematical speed limit required to chop continuous reality into digital pieces without breaking it. Passing signals and systems requires recognizing that the equations on the page are just representations of geometric transitions. In the time domain, you visually slide and integrate waveforms to track how a system applies its footprint over an input. In the complex frequency domain, you verify stability by plotting exact pole coordinates and confirming the region of convergence swallows the unit circle. And in the frequency domain, you protect the integrity of a digitized signal by strictly enforcing the Nyquist sampling rate to prevent spectral collision. If you adjust your convolution limits as Ilvanov changes, and if you verify your pole locations before applying steady-state theorems, you avoid the traps that cause the highest failure rates. By anchoring the calculus to these 5 geometric frameworks, you strip away the academic bloat. You possess the exact analytical blueprint needed to clear the exam and to build predictable systems.